right, so here we are coming to the end of the topics in Gen Chem 2, and we're going to talk about um, the, the big daddy of thermodynamics. It's called free energy or Gibbs free energy, and we're going to relate this now back to both. We're going to relate it back to both enthalpy and entropy as well as temperature. So we used these laws of thermodynamics in our discussions before, talking about the first law where energy cannot be created and destroyed, the second law where the total entropy is moving towards positive, and the third law for a perfect crystal to be at absolute zero, the absolute entropy has to be zero, so no movement. So Gibbs free energy, right, is something that we can use to show whether or not a system is spontaneous. Okay, and if we start with the fact that a spontaneous system is increasing the entropy of the universe, we can look at that first equation. And we can show that it's related to delta H of the system minus T delta S of the system. And we can then talk about Gibbs free energy. It's the maximum amount of work that can be released to the surroundings by a system. So we've got some, things that we have to hold constant, like temperature and pressure. But it's called the chemical potential because it's pretty much how much stored energy there is in a system. All right, so now we can replace that minus T delta S of the universe as delta G of the system because that's what can be, again, given off. And so delta G of the system is now equal to delta H minus T delta S. So the delta S of the universe determines whether its process is spontaneous, then it in turn means that delta G is now also determined spontaneity. So a negative delta G, right, because if you look at this term up here, it's a negative, right? So a negative delta G is a spontaneous system. So here's delta G is negative, right? It's a spontaneous system when it's negative. Delta G will be negative if delta H is negative and delta S is positive. Again, the equation that I just wrote at the top there, delta G equals delta H minus T delta S. Well, if delta H is negative and delta S is a positive, then you always return a negative, right? When delta H is negative and it's large and it overcomes any contribution of delta S that might be negative, then delta G will also be negative. And then the opposite, right, of when delta H is positive, but delta S is so large and positive that it can overcome and create a negative delta G. Okay? So delta G is always positive when delta H is positive and delta S is negative. It's never ever going to be spontaneous at any temperature. The rest of these are temperature dependent except for the very first one. When delta G is zero, the reaction is at equilibrium. That'll come into play later. So here are those different scenarios, right? Where delta H is negative, delta S is positive, it's always spontaneous, right? Okay, so an example would be N2O going to N2 and O2. The non-spontaneous is where delta H is positive and delta S is negative, always non-spontaneous. The negative negative, right? It is spontaneous when the negative of delta H is greater than the negative in the no, I'm sorry, the negative in the delta S. Okay, so delta H negative overcomes uh, the term T delta S being a positive. Okay, because that's going to be a negative T, right, times a negative delta S, meaning that that will be a positive in the third one there. And then finally, the last one where the delta H is now the positive factor, right? And the positive from the S returns a negative, and so as temperature goes up, right, it's going to be spontaneous. So let's look at some calculations. Start with this reaction, carbon tetrachloride going to carbon and chlorine, and it has a delta H of 95.7 positive, has a delta S of positive 142.2. So now this is a positive positive. It says at 25 degrees C. Calculate the delta G and see if it's spontaneous. First thing we have to do is we have to get all our terms in the same, right, the same units. And so we've got one of them in kilojoules, we've got one of them in joules per K, and then we've got one of them in degrees C. Right, so we go first to K, and then down here we go to joules for the delta H, and it turns out that this is going to be positive, right? So if it's positive, the reaction is non-spontaneous at that temperature. Here's another one, right? Al plus Fe2O3 going to Fe as a solid and Al2O3 as a solid. So the delta H is a minus 847.6, the delta S is a negative 41.3, and it's at 25 degrees C. So again, we've got these terms, kilojoules and degrees C, and we're going to have to deal with those. So here's where we do it, 298, and change this one to joules, and sure enough, you get a negative. All right, so it is a spontaneous reaction. We can also look at these problems and say, okay, when is it not, right? Okay, so when in the previous example, when is it non-spontaneous? We could look at the first example, the CCl4, and say, when is it spontaneous, right? Because we can tell that at that temperature it wasn't going to be, but with a positive delta S, we have the potential. So at 673 K, right, that means that it will be spontaneous because we're getting a zero, right? Or what we want is a negative, and so it's got to be temperatures greater than 673. Okay, so how did we do that? Well, we plugged into this and said set basically set delta G to zero, right, in that equation. Again, these are the conversions. You got the joules, you got the joules per K. The temperature is going to be in Kelvin. And then we just solve for temperature. Another example, so here this is saying where will it, the maximum temperature, it will be spontaneous, right? So again, going back to that aluminum and iron problem. Again, the same thing. We basically set delta G equal to 0, plug in the other numbers, and solve for K. Okay, don't be thrown by the fact that they're using the greater than and less than symbols. You really are just saying, where is it 0, right? And then any temperature above is what we're going to solve for. And so again, we solved right here at 1775 degrees C. Okay, so we can apply Hess's law basically, right? And there it is. Delta G of a particular reaction is equal to the summation of the products minus the summation of the reactants, taking into account the stoichiometry. That's at 25 degrees C. At temperatures other than that, we can again apply the equation and change the temperatures. And then we can also, if we do it for each reaction, then we can look at a delta G total for each individual reaction. So another kind of application of Hess's law. So let's see how we apply that. And ooh, that's all jumbled. We'll have to work that out in class. So we can also do these standard free energies of formation. And you've seen that in our delta H and delta S discussions. So we've got delta G of formation, and you get the little um, zero there. And so these are all of the standard molar free energies of formations for all these different elements. And so we can combine those. Again, using that Hess's law, where you're summing up the products and subtracting the summation of the reactants and making sure that we abide by stoichiometry. So here's an example. The reaction is given, and you can look up all of these substances in that table. So these are the substances I'm talking about. You look them up in that table, and you plug them in. Don't forget an 8 there, even though it's not going to change things. You got a 4 there, you got a 2 there, right? These are just 1, and so they go straight in. And then you look down here, and here's the 2. There's the 8. And I don't see where they did the 4. Yeah, they should have done a 4 here. Okay. So let's look at this one. And again, H2O. We know now that O2 or any element in its elemental form is 0. But then we can look up H2O and H2O2 and H2O2 as products minus H2O as reactants. So there's products, there's reactants. There it is. So a lot like what we've looked at with these other state functions, if you can set up a series of reactions to get the delta G values, then the delta G total is a sum of those values. If the reaction is reversed, as we've seen before, where we reverse to get some things to subtract out, then the delta G value just reverses. If it's multiplied by a specific factor, again, to make sure that things cancel out on one side or the other, then the delta G has to be multiplied by the factor. So here's an example of that, where you've got carbon, hydrogen going to C3H8, and you've got these different reactions that you can find in that table or in a table. And so you have to convert, you have to change them to get things to cancel out. You have to reverse that first one because C3H8 is actually the product you're looking for. Once you reverse that, you can look at the other ones and see where they fit into this. And what you can get out is you can get out this delta G of minus 23. We can do the same thing with the H2O going to H2O2. Oops, we can do. So, what's the free about free energy? Well, it's the maximum that can be released from a system, right? And a lot of exothermic reactions, the heat released goes into the entropy of the surroundings, so it's really not available to do much work. And even if some of that free energy is lost to heating, then it's not able to be used. And so the free energy is actually the energy that is useful. So if we examine all of this, where we know that we have an exothermic process, um, where does it go, right? Where does some of that heat um, happen to go? Well, it goes into heat energy and an increase in entropy of the surroundings. So we can relate delta G to K. If you remember, we said delta G is 0 at equilibrium. And so we have to talk about a few things here where delta G is equal to the delta G at standard states only when everything is in standard states. But under non-standard conditions, then there's a different factor here, right? Because Q, is the reaction quotient. And so we have to put in this factor that actually changes where the delta G is. But then we can also look at this and say, okay, well then delta G0 is equal to minus RT ln K. So now we have some idea of how to decide which way the reaction is going to go with putting delta G into the mix. So at equilibrium, delta G of a reaction is 0. So this is equal to negative RT ln K. When K is less than 1, delta G is positive, and the reaction is spontaneous in the reverse direction under the standard conditions. When K is greater than 1, delta G is negative, and the reaction is spontaneous in the forward direction under standard conditions. And when K is equal to 1, delta G is 0, and the reaction is at equilibrium. Again, this is all under these standard conditions. All right, so this is the way it looks in a kind of a graphical format, if you will, right? When A goes to B, if we're looking at less than 1, well, the reaction has to reverse to actually get to equilibrium, and so it is going to be spontaneous in that direction. When it's greater than 1, it has to go forward to get to equilibrium, and so it is spontaneous in the forward direction, but when it's at equilibrium, um, delta G is 0. So we can use this delta G equal to minus RT ln K to do some calculations. And here's one. Calculate K at 298 for a reaction. You go and look at what the delta G is, and you plug all of these things in, and you have the K of the reaction, and you can plug that in, and you can come up with 0.32 to find the K. I'm sorry, you don't have the K of the reaction, but you're trying to calculate the K of the reaction. You have all these other, right? This is just R, 8.314. This is T, right, which is 25 degrees C. That's standard state, right? And this is the calculated delta G. So first, use this information from the appendix and use this delta G Hess's law version, and you get this 2.8 kilojoules, right? And because this is in joules, you convert it back to joules. You put all this together again, and you get the K is equal to 0.32. Remembering that the anti-ln is um, e to the minus, right? One more of these. We can estimate the equilibrium constant for this reaction at 300, or I'm sorry, at 700. Here it is. Um, you can, you're given The delta G, you're told it's at 700K. You have 8.314, and you come up with minus 7.97. And again, plug that into e to the minus 7.97. You get 3.5 times 10 to the minus 4.